Welcome to the deep dive. Today we're plunging into something really fundamental, numbers.
Yeah, the absolute building blocks of math, how they work based on these notes and definitions you've got.
Exactly. And our mission really is to cut through maybe some of the confusion and give you a kind of shortcut.
Like a clearer map, maybe, understanding the basic landscape of arithmetic.
Yeah, the types of numbers, their properties, maybe some quirks along the way.
Sounds good. It's foundational stuff, but it dictates everything else, really.
Okay, let's dive in then. Your notes lay things out quite neatly, starting with the natural numbers.
Right. 1, 2, 3. The ones you count with. Simple, straightforward, one's the smallest.
Then you just add one thing, 0.
And boom, you've got whole numbers.
Yeah.
0, 1, 2, 3. Seems tiny, adding 0, but matters later.
Okay, and then we need more.
Well, yeah. Think about subtraction. Let's say 2 minus 5, not a whole number.
Right, so you need negatives?
Exactly. That brings us to integers. You get the negatives, -2, -1, plus the 0, and the positives, 1, 2. Stretching out both ways. No smallest, no largest.
Makes sense. You need them to make subtraction always work, basically.
Pretty much. And we keep going. The next layer is rational numbers.
Okay, rationals. That sounds like fractions.
Yeah, basically any number you can write as a fraction, ab, where a and b are integers, and crucially, b isn't 0.
So that covers integers, right? Like 5 is just 51.
Correct. And obviously fractions like 34 or decimals that stop like 0.5.
Or decimals that repeat, like 0.333.
Yep, 0.3 recurring is 13. So that's rational too. It's a huge category.
But not everything fits.
Nope. That's where the irrationals come in. Numbers you can't write as that simple fraction.
Like the famous ones, square root of 2.
Exactly. Or root 7, root 15. Or even combinations like 3 times root 5 or root 5 plus root 3. Your notes point those out.
And their decimals just go on forever without repeating.
That's the key. Non-terminating, non-recurring. But watch out, like your notes say, root 16 is just 4.
So it simplifies to a rational. Sneaky.
It can be. So you have rationals, you have irrationals, and put them all together.
That must be the real numbers. Everything on the number line.
That's it. Every real number is either rational or irrational. That's kind of the basic map.
Okay, got the types. But your notes also dig into kinds of numbers within those types, like primes.
Right. Back within the natural numbers, mostly. A prime number is greater than 1 and only divisible by 1 in itself.
Like 2, 3, 5, 7.
Yeah. And 2 is special. It's the smallest prime and the only even one. Everything else is odd.
And if a number greater than 1 isn't prime?
Then it's composite, like 4, 6, 8, 9. They have more than 2 factors. 4 is the smallest.
And number 1 is just neither?
Yeah, it's just unity. Doesn't fit either definition. The notes also mention some cool pairs.
Oh, yeah. Like what?
Twin primes, prime numbers just 2 apart, like 5 and 7 or 11 and 13.
And co-primes?
Those are pairs of numbers whose only common factor is 1. They don't have to be prime themselves, like 10 and 21. They share no factors other than 1.
Huh. Interesting relationships. Your notes also had these divisibility tests, like shortcuts.
Yeah, they're handy. Ways to check if a number divides by another without actually doing the long division.
Like checking the last digit for 2, 5, or 10.
Exactly. Ends in 0, 2, 4, 6, 8. Divisible by 2. Ends in 0 or 5. Divisible by 5. Ends in 0. Divisible by 10. Simple.
And there were ones for 3 and 9 using the sum of the digits.
Right. Add up the digits. If the sum is divisible by 3, the number is 2. Same for 9, like 123. 1 plus 2 plus 3 is 6. 6 is divisible by 3, so 123 is...
Clever. Okay, shifting gears slightly, what about working with irrationals? There's this thing, rationalization.
Yes. Sometimes you have an irrational number, maybe in the denominator of a fraction, and you want to make it rational.
How does that work?
You multiply it by its rationalizing factor, or RF. That's another irrational number, often related, such that their product is rational.
Like the example in the notes, 2 plus 3 times 2.
Perfect example. That multiplies out using the difference of squares to 2 squared minus root 3 squared, which is 4 minus 3.
Which is 1, and 1 is rational, so they're RFs of each other.
Exactly.
Right.
Or simpler, root 3 times root 3 is just 3, so root 3 is its own RF. It's a neat trick, especially for simplifying fractions.
Okay, makes sense. Now, the really deep stuff. The properties of how these numbers behave with operations, like addition, subtraction.
Yeah, the fundamental rules. Closure, commutativity, associativity, distributivity. Your notes cover these across different number sets.
Let's start with closure. That just means if you perform an operation on numbers within a set, the answer is also in that set, right?
Precisely. But the interesting bits are where it fails. Natural numbers, for instance. Add 2 naturals, you get a natural, multiply them, same, but subtract. 3 minus 5.
Not a natural number, not closed under subtraction. Same for division, like 3 divided by 2.
Right. Whole numbers are the same, not closed for subtraction or division. Integers fix subtraction. They are closed for that. But division, 3 divided by 2, is still not an integer.
Ah, so integers aren't closed for division. What about rationals?
They're pretty robust, closed under addition, subtraction, multiplication, and division. Except
Division by 0. Can't do that.
can't do that. That's always undefined. But otherwise, rationals are closed.
Okay, what about the other properties? Commutativity. Order doesn't matter.
Right. A plus B equals B plus A,
Sure.
and AB equals BA. That works for addition and multiplication across these sets.
But not subtraction or division. 5, 3 is not 3, 5.
Definitely not. And 6, 2 is not 2, 6. So subtraction and division are not commutative.
Got it. Associativity. That's about grouping, isn't it?
Yeah, A plus B plus C, A plus B plus C. And the same for multiplication. Grouping doesn't change the result for addition or multiplication.
And again, probably not for subtraction or division.
Correct. They aren't associative either. The order you do them in matters.
And finally, distributivity.
That's how multiplication interacts with addition or subtraction. AB plus C equals AB plus AC. Multiplication distributes over addition, and subtraction too.
Okay. And the notes mention 0 and 1 having special roles.
Yeah, the identity elements. 0 is the additive identity. Add 0 to anything, it doesn't change. A plus 0 equals A.
And 1 is the multiplicative identity. A 1 equals A.
Exactly. These properties seem basic, maybe even obvious, but they define the structure, and seeing where they don't apply, like closure failing.
That tells you why we needed to invent or discover these bigger sets of numbers, like integers and rational.
I think so, yeah. It wasn't arbitrary. You hit a problem. You can't always subtract natural numbers and stay natural, so you expand the system to solve it.
So, reflecting on all this, the different number types, the rules they follow, the times they don't follow the rules in certain sets, what's the big takeaway here?
Well, thinking about that very point, how limitations, especially with closure for subtraction and division, force the creation of integers and rationals, what does that tell you about how mathematics itself might be built? Is it just a fixed set of truths, or is it something that grows and adapts, driven by the need to solve problems and make operations work consistently, something to chew on?